Uh, Thank you and thanks a lot and for inviting me for this conference. So, good morning. My name is Mamtani, and I'm excited to present our research titled "Integrating Graph-Based Representations with Deep Contextual Models" as a part of NLPA 2025. This work explores a hybrid approach to text classification that brings together the power of structural learning using graph convolution networks and deep contextual understanding of transformer models like BERT. Let's deep dive into it. So background, yeah. To set the context, let's briefly go over the components. First, text classification is a fundamental task in NLP where we assign predefined labels to text, such as topics, sentiments, or intents. It's widely used in practical applications like spam detection and news categorization. Now let's look at the models. Distill BERT. It's a lighter and faster version of BERT. It captures deep contextual semantics by leveraging pre-scale, large-scale pre-training. And despite being more efficient, it still retains much of BERT's language understanding power. GCN, on the other hand, are designed for graph structured data. They are particularly good at capturing structural relationships between words. So, in simple terms, BERT gives us deep language context and GCN gives us structural insight. Our idea is to bring them together. So, now that we have covered the background, let's cover the motivation of this work. Our key goal was to enhance text classification by leveraging both semantic and structural representations in a single unified model. We used DistilBERT to extract deep contextual embeddings, allowing us to understand the meaning and nuance of language. On the other hand, we built document word graphs to model the structural dependencies, such as how frequently words appear together across a corpus. The idea is to combine the strengths of transformers and GCNs. While transformers are excellent at capturing semantic context, GCNs are better at capturing relational structure in the form of graphs. Many prior models focused only on one of the aspects, but by integrating both of them, we aim to improve performance while maintaining efficiency and interpretability. So yeah, let's see the prior work. Like let's walk through some of the existing approaches that were there earlier. First, early models like TF, IDF combined with traditional classifiers such as SVMs, LSTMs were widely used and did well. But these approaches lacked the capacity to capture deep semantics or relational structure in text. Then came contextual models like BERT and DistilBERT, introducing introducing transformers-based architects that capture deep and context our embeddings. These models brought a huge leap in performance for many NLP tasks. Separately, we also had structured models like text GCN, which used graph convolution networks to capture global document word relationships across like using graph-based learning. More recently, hybrid approaches like BERT GCN, Robota GCN have combined these two strengthens semantics from transformers and structure from GCNs, leading to improved performance, but often at the cost of higher computational requirements. This brings to our contribution. We proposed a lightweight hybrid model that fuses DistilBERT with GCN using a simpler fusion strategy, that is concatenation, and significantly fewer parameters. The result is a model that's both efficient and performant, making it better suitable for real world deployment scenarios. So yeah, let's walk through the model architecture. We start with two parallel components. First one is graph neural network and second is digital bot. In the top half, we can see that GCN pipeline where we construct a document word graph. Here documents and words are nodes, edges capture co-occurrence relationships. We pass this graph to GCN to compute structural embeddings for each document. On the bottom half, we use DistilBERT to extract contextual embeddings from raw text. DistilBERT provides deep semantic representations capturing the nuances of language. These two streams produce two different embeddings for each document, one from GCN and one from BERT. In the aggregation layer, we simply concatenate these two embeddings. This gives us a unified representation that captures both structure and semantics. Finally, we pass this representation through a fully connected classification layer with softmax, which predicts the label for each document. Yeah, so now we will see the first distillbut layer extraction. To generate contextual embeddings, we used the pre-trained distillbut model, which is a lighter and faster version of BERT. We first fine-tuned this model on 20 newsgroups dataset to make sure it understands the language and structure of our domain. After fine-tuning, we extract the embedding from the CLS token, that is the last layer of before the classification for each document. This gives us a 760 dimensional vector that summarizes the semantic content of the entire document. These embeddings are used for as a fixed feature vectors, and we don't update distillbut any further when we train the GCN. This makes our pipeline more efficient and less computationally intensive, while still benefiting from rich contextual understanding that transformers provide. So now we'll see how we'll construct the graph. Uh, we built a heterogeneous graph where we create two types of nodes. One type is document node for each document in the corpus, and the other is word node for every unique word in the vocabulary. Once these nodes are created, and then we define the edges. There are two type of edges in this graph construction. First one is word edges. These connect two word nodes if they co-occur while within a sliding window across the entire corpus. This edge weights are determined using point-wise mutual information, that is PMI, which measures how strongly two words co-occur compared to what they have expected by chance. This helps us capture global co-occurrence structure among words across all documents. Second type of edge is document word edges. Each document node is connected to the word it contains, and the edge weight is based on the TF-IDF, which captures how important a word in a specific document related to the entire corpus. This helps a model to maintain the local content relevance. Together, these edges help encode both global and document specific context into the graph, uh, which is then used for GCN based learning. Now we have seen how the graph is constructed with local and global relationships. Let's see how we can pass this graph to GCN. We feed this document word graph into a two-layer GCN network. This step is crucial because it let us go beyond simple graph structure, and we start capturing how information flows across the entire graph, enabling rich document representations. The GCN has two main inputs. First is the adjacency matrix, which encodes the edges between nodes. This includes PMI based word connections and TF-IDF based document word links. Second is the feature matrix, where we initialize each node in a graph using a one hot encoding, essentially giving each node a unique identity at the start. So in our model, we used a variant learnable GCN. Here, instead of fixed adjacency matrix, we learn this adjacency matrix, and we introduce a trainable parameter alpha that mixes the original matrix A and the normalized counterpart A hat. So this matrix is learned during the this gives the model the flexibility to learn how much it wants to rely on raw structured versus normalized structure, allowing better adaptability across datasets. So this A matrix will adapt according to the dataset and during the training. The main update rule is the equation shown on the slide. At each layer, the hidden state H of each node is updated by aggregating information from its neighbors. The degree matrix is used to control the influence from the high degree nodes, which are these neighbors. That transformation is passed through a trainable weight matrix W, which is learned during the backpropagation, and a non-linear activation function ReLU. After two layers of such propagation, we obtain updated node representations, and we take the embeddings of the document nodes only as a structural embedding of each document. This embedding reflects not just the document's local word usage, but also the global word co-occurrence patterns. Moving to next slide. So yeah, now we have seen the embeddings, both from Distilbert and the GCN. The next part is how we can effectively combine the embeddings. So one simple, so we did three experiments in this research, and first one is simple concatenation. Here we take the CLS token output from Distilbert, which is 768 dimensional vector, and concatenate it with the 200 dimensional vector embedding vector obtained from GCN. This gives us the final fused representation of 968 dimensions. It's important to note that the approach has no learnable parameters. It's just a raw concatenation of two embeddings. So mathematically, we just take the two vectors and concatenate at the end of the other one. Interestingly, this fusion method gives the best performance among all the strategies we will see. The second strategy we tried is element-wise summation. So to do this, we first reduce the 760 dimensional bird embedding down to 200 dimensional using PCA, and then added it element-wise to the 200 dimensional GCN embedding. This approach keeps the final vector compact and balances both sources of information. However, since PCA can discard important semantic features, we see a slight drop in performance compared to concatenation. So the third fusion method introduces a bit more flexibility. We learn a scalar lambda between 0 and 1 to automatically weight the contribution of each embedding, but still button GCN. So this approach is learnable and tunable, which sounds great, but in practice it's still underperformed compared to simple concatenation. So even though it's adaptive, it adds complexity without clear gains in this case. So for final classification, we use the fusion strategy one, that is concatenation, as it gave the best results in our experiments. After fusion, we concatenated the 768 distilled embedding with 200 GCN embedding to get 968 vector. This combined embedding is passed through a fully connected dense layer and followed by softmax layer to predict the document class. During training, we used cross entropy loss as our objective. One important design decision is that we freeze the Distilbert parameters after initial fine-tuning and only update the GCN and the final classification layer. This makes our training a little bit more efficient and less memory intensive, especially for small data sets. Yet we still benefit from rich contextual and structural information that both modules provide. So the datasets that we used is 20 NG news group dataset. It's popular benchmark dataset of around 18,000 news articles spread across 20 classes. We chose this dataset for its diversity and structure, and also it is very widely used in prior hybrid modeling work. So it provides a solid ground for comparisons. So the training setup, we fine-tuned distill bird initially, then froze it during training. The GCN and classification had wet trained using atom optimizer with a learning rate of around 10 power minus 5. We used early stopping and cross entropy loss to ensure stable convergence of this GCN during training. So the results that we obtained are, uh, as you can see in the chart, distill but alone gives the highest accuracy of around 70%, establishing a strong contextual benchmark. However, that's the only part of the story. Our hybrid model, which combines distilled but and learnable GCN, that's also achieves almost 70%, just marginally below, but it brings in graph-based structural awareness that's distilled but lacks. This structural component adds the interpretability and generalization capacity, especially in scenarios where understanding relationships across documents and terms matters. When tested in isolation, static GCN and learnable GCN achieve 67 and 67% respectively, proving that structural signals alone are valuable but not sufficient. Among fusion strategies we explored, Concatenation clearly outperforms summation and training weighting. It preserves the full semantic and structural richness of both representation without introducing additional tuning complexity. What's also worth seeing is that our model is lightweight, thanks and yet matches the performance of heavier models while offering greater explainability and structural aware learning. So the trade-off is both efficient and interpretable. Now let's compare with the earlier approaches. Our model outperforms traditional baselines like LSTM and PVDM, which lack the capacity to model deep contextual and structural relationships. So we address this gap by integrating graph-based learning. Second, we deliver results that are competitive with early BERT-based models despite using smaller and more efficient components. Our hybrid architecture combining distilled BERT and learnable GCN achieves nearly the same accuracy as larger models like BERT GCN, Robota GCN, while using fewer parameters and significantly less compute power. State of art models like BERT GCN and Robota GCN reach higher accuracy, around 89%, but this comes at the cost of heavier transformer backbones, complex fusion models, and increased GPU and memory time, training time. In contrast, our model uses distilled, which is a compressed transformer and a two-layer learnable GCN, resulting in a much lighter and computational footprint and faster inference time without sacrificing too much on performance. So we can say the overall takeaway is like we might give up on a small amount of accuracy. Our model offers a balanced and resource efficient uh, technique, making it very suitable for real world deployment where scalability and transparency are the key. So now we see the limitations of of the current work and what we can do better in the future iterations. First, we observed that adding deeper GCN layers led to overfitting. The model complexity increased, but without any meaningful gain in the performance. So for our tasks, we use two-layer GCN to be optimal. Second, the 20 news groups dataset we worked is on fully labeled. While it's a good benchmark, it limits us from evaluating our model's performance in a semi-supervised or low resource setting environment, which is little bit of more realistic in our application in many applications. Looking ahead, there are several exciting directions to explore. First, we try graph attention networks. This allow the model to learn which neighbors are more important, essentially weighting edges dynamically, which could improve performance. Second, we plan to use fast GCN, which are inductive GANs, designed to scale to large graphs and can generalize better to unseen data. And finally, we want to move beyond 20 ng and evaluate on larger and more diverse datasets to test the robustness of our model. While our current model is solid, there's a clear path to extend it work in more flexible and scalable ways. So, in conclusion, we proposed a hybrid text classification framework which combines the strengths of two powerful models, GCNs and for structure embedding and DistilBERT for deep contextual semantics. By fusing these two representations, our model improved classification performance while remaining lightweight and interpretable. Although it may not outperform the absolute state-of-art models like BERT GCN, Robota GCN in raw accuracy, it offers a much more efficient and resource-friendly alternative, making it a strong candidate for real-world deployments where compute and explainability matters. Looking ahead, we can see that integrating attention mechanisms such as graph attention networks or attention-based fusion layers presents a good direction to further enhancements and performance and little bit uh, s- even surpass the more complex baselines. So overall, this work opens a practical and uh, good path towards combining structural aware learning and deep semantics in NLP. Yeah, thank you.